A stunning look into the distant universe, James Webb brings the unimaginable into view. NASA's James Webb Space Telescope has just unveiled its first jaw-dropping images from the deep cosmos, offering us a glimpse of galaxies so distant, they date back to the dawn of time. For the first time, those galaxies far, far away feel a little closer to home. When Webb turned its golden mirrors toward what looked like a quiet, unremarkable patch of sky, no one expected what came next. The telescope locked onto a galaxy over 13 billion light-years away, existing just a few 100 million years after the Big Bang. But instead of finding a fledgling, chaotic system, Webb captured a fully-formed galaxy with intricate spiral arms and a supermassive black hole at its center. This discovery shook everything we thought we knew about the early universe. Before we dive deeper, hit that like button and subscribe for more cosmic updates. This galaxy wasn't supposed to exist. At least, not yet. According to current models of cosmic evolution, complex structures like this shouldn't have taken shape so early. The universe, still in its infancy, should have been a turbulent place of scattered gas and star nurseries. And yet here it was, a mature, well-organized galaxy that looked billions of years older than it should. Webb's infrared vision allows it to peer through cosmic dust and detect the redshifted light of the universe's first galaxies, light that has been traveling for eons. Unlike the Hubble Space Telescope, which mainly sees invisible and ultraviolet light, Webb can see deep into time, revealing secrets the cosmos has kept hidden until now. What it found was staggering, a massive object not only showing early galactic maturity, but also packed with heavier elements like carbon, oxygen, and traces of iron, signatures that multiple generations of stars had already been born and died in rapid-fire succession. That's like watching a baby grow into an adult in mere moments, skipping childhood entirely. Even more mind-blowing? The supermassive black hole at this galaxy's core, over 1 billion times the mass of our Sun. According to our best theories, black holes this massive take billions of years to grow. But this one seemed to appear almost instantly, fully formed. This discovery sent shockwaves through the scientific community. Either our understanding of early galaxy formation is missing something major, or unknown forces were at play in those ancient days. One compelling theory, dark matter, usually seen as a silent, invisible background player, might have taken a lead role in early galaxy building. These dark matter clumps may have created a cosmic framework, helping matter organize faster and more efficiently than expected. If true, this could change how we view dark matter entirely, not just as a shadowy presence, but as a master architect of the universe's earliest structures. A new look at the universe's wild youth. Was the early cosmos more creative than we thought? One emerging possibility is that the early universe was far more turbulent and productive than scientists had imagined. Not just a hot mess of particles, but a fertile, energetic environment where chaotic fluctuations after the Big Bang may have jump-started regions of intense star formation. These so-called starburst nurseries could have rapidly churned out stars and even planted the seeds of supermassive black holes, almost as if the cosmos hit fast forward. And yet, even these revised ideas fall short of fully explaining what James Webb uncovered. This wasn't a one-off discovery. Webb didn't just spot a single unusual galaxy. It found multiple ancient galaxies across different corners of the sky, all showing signs of unexpected maturity and structure. That meant this wasn't a rare anomaly. It was likely a common feature of the early universe. It turns out the young cosmos was far more ambitious than we ever gave it credit for. Massive galaxies, dense with stars and brimming with complex architecture, were forming during a time we once believed was dominated by primordial fog and chaos. Thanks to gravitational lensing, where massive galaxy clusters act like magnifying glasses in space, astronomers got a clearer look. These cosmic zoom lenses amplified the light from these distant galaxies, revealing stunning detail: glowing gas tendrils, rotating spiral arms, and intricate dust lanes. These were features thought to appear billions of years later. But there they were, shining from nearly the dawn of time. These revelations reignited debate about the inflationary model, the theory describing the universe's exponential expansion moments after the Big Bang. Some scientists now wonder, did that initial burst of growth plant more intricate seeds than we realized? Could hidden zones of spacetime have offered ideal conditions for matter to organize unusually fast? Maybe the Big Bang wasn't as uniform as we thought, despite what the cosmic microwave background tells us. What Webb uncovered paints a far more layered and possibly intentional picture of the universe's beginning. To add another twist, Webb also detected chemical signatures that shouldn't have been there so early, traces of water vapor, carbon dioxide, even organic molecules. Normally, we expect such ingredients to form much later, through long cycles of stellar birth and death. Yet here they were, already swirling in galaxies born just a few 100 million years after the Big Bang. Far from being barren clouds of dust, these galaxies were already brewing the ingredients for complexity, and maybe even life. And then came the light fluctuations. In the background glow around some of these galaxies, Webb picked up strange variations, ones that couldn't be chalked up to gravitational lensing or known cosmic background patterns. Some scientists believe they might be the first light-based evidence of gravitational waves, ripples in spacetime caused by cataclysmic events like black hole collisions or galaxy mergers. If confirmed, it would offer a completely new window into the violent, energetic activity of the infant universe. With each discovery, traditional theories began to buckle under the weight of new data. That's when bold new ideas entered the conversation, including one particularly mind-bending proposal. What if our understanding of time itself is flawed? Under the intense conditions of the early universe, time might have flowed differently. What seems like an instant to us might have stretched out far longer locally, masked by relativistic effects we're only beginning to grasp. This idea remains highly speculative, but it's already igniting debate in cosmology, quantum physics, and even the philosophy of time. The James Webb Space Telescope was built to unlock the secrets of how stars, galaxies, and even the cosmos itself came to be. Instead, it's left astronomers grappling with questions bigger than the ones it was built to answer. Within its first deep-field snapshots, Webb spotted fully formed galaxies and gargantuan black holes at distances we never thought possible. This isn't just finding older objects, it's witnessing a brand new chapter in the universe's youth, one that seems to upend our most trusted cosmological playbook. Imagine pointing a superpowered mirror at what you expect to be dusty embers, then seeing gleaming skyscrapers instead. That's exactly what Webb did. It peered into the ancient dark and discovered mature, complex systems thriving when the universe was barely a toddler. This cosmic curveball forces us to rethink everything, from how quickly stars can live and die, to whether dark matter played a more active role in early structure building, or if unknown forces sculpted spacetime itself. Even more astonishing is how common these early heavyweights appear to be. Webb has catalogued so many massive young galaxies that it's clear this wasn't a one-off coincidence. It was a defining feature of the universe's early days. Suddenly, primitive and chaotic feels like an understatement. The infant cosmos may have been astonishingly productive. Webb's infrared instruments, NIR-SPEC and MIRI, are like time machines, catching faint echoes of starlight that traveled 13 billion years to reach us. Every photon challenges a well-worn theory, revealing a cosmos richer, deeper, and stranger than anyone dared predict. When Webb gazes at a galaxy from 13 billion years ago, it's not just looking across space, it's looking back in time. And what it sees isn't the murky primordial soup we imagined, but a bustling workshop of matter, form, and even the raw ingredients for life. One standout finding, a galaxy at extreme redshift rotating like a modern spiral, complete with a flat velocity curve. In today's universe, we explain that with dark matter halos. But for such halos to exist so early, they'd have had to form and stabilize at lightning speed, rewriting our timelines for how structure takes shape. With each new dataset, Webb isn't just extending our view, it's rewriting the narrative of the cosmos. If these revelations are any indication, we're only at the prologue of a story far more spectacular than we ever imagined. But this opened up a whole new mystery. If dark matter halos were already so developed at such an early stage, they must have collapsed and stabilized incredibly fast. That raises big questions. Was dark matter not only more abundant back then, but also more interactive than we ever imagined? As if that wasn't enough, the James Webb Space Telescope uncovered something even stranger. It detected unusual spectral lines in several ancient galaxies, signals that didn't match any known elements or typical cosmic processes. They weren't caused by hydrogen or helium, which usually dominate early cosmic chemistry. Some scientists suggest these strange signals might be clues of exotic particles breaking down, possibly involving elusive entities like sterile neutrinos or particles from the mysterious dark sector. Others believe they could be early fingerprints of quantum gravity, revealing effects only possible in the extreme environments of the newborn universe. At the same time, Webb spotted vast, empty voids surrounding these early galaxies, regions completely devoid of light. According to existing models, the universe should have still been fairly uniform at this point. But these massive bubbles imply that matter had already begun clumping and separating on a dramatic scale, much faster than simulations had ever predicted. It's as if the cosmos didn't gradually warm up. It was already boiling, long before we expected the heat to be turned on. Adding to the intrigue, Webb found intense ultraviolet radiation surrounding some highly energetic ancient objects. These powerful emissions couldn't be explained by star formation alone. Their brightness, pattern, and placement pointed to unknown sources, perhaps ultramassive stars or quasars that lit up far earlier than theory allows. If quasars, powered by supermassive black holes devouring matter, were already this active, it means those engines were running at speeds we didn't think possible. Things got even more puzzling when X-ray data from other telescopes, like Chandra, lined up perfectly with Webb's deep-field views. Galaxies from more than 13 billion years ago were also shining brightly in X-rays, evidence of central powerhouses, likely active galactic nuclei, blazing with energy at redshifts beyond 10. What this suggests is profound. The early universe wasn't just forming stars, it was already engaging in fierce, high-energy processes typical of much more mature galaxies. Webb also revealed something even more startling. Subtle distortions in spacetime, seen through patterns of gravitational lensing, hinted at the possible presence of cosmic strings. These hypothetical defects, believed to have formed in the earliest moments after the Big Bang, could bend light and leave deep imprints on the cosmic microwave background. Some of the lensing data matched what we'd expect from such strange features, but more evidence is needed. And then came another surprise: massive star clusters orbiting these ancient galaxies. They looked eerily similar to today's globular clusters, dense, spherical gatherings of old stars, but they were appearing far earlier in the cosmic timeline than expected. Globular clusters are usually considered ancient leftovers from the early days of star formation. But finding them in such numbers, and in such a developed state, so soon after the Big Bang forces a rethink. Even their metallicity, the presence of heavier elements, didn't match what theories predicted for that age. Instead of being poor in heavy elements as scientists expected, these star clusters showed early signs of chemical enrichment, hinting that stellar material was being recycled far more quickly than our current models allow. Using its powerful coronagraph, Webb was able to block the blinding light from several bright early galaxies and peer into their outer regions. What it uncovered only deepened the mystery. Faint, thread-like structures, filaments made of gas and stars, were stretching far beyond the galaxy's central cores. These cosmic strands pointed to massive streams of cold gas flowing inward, likely fueling the rapid bursts of star formation seen in their centers. But their presence at such an early time in the universe is difficult to explain. The conditions needed to form these features, including cooling processes, gravitational instabilities, and favorable environments, weren't supposed to exist yet. Even more surprising, these filaments appear to be magnetized. Polarized emissions observed in some spectral bands suggest the presence of organized magnetic fields. That's a puzzle in itself. Magnetic fields are notoriously hard to explain in cosmology. We still don't fully understand how they form, grow, or align. And yet, here they are, magnetic structures woven into a universe just starting to take shape. Some scientists propose these early fields could be the result of unknown plasma behaviors or even relic imprints from before the Big Bang, carried forward by quantum fluctuations. If proven, it would rewrite our understanding of cosmic magnetism. Webb also delivered stunning insights into the temperature dynamics of these galaxies. With its MIRI, mid-infrared instrument, astronomers mapped out the heat signatures of dust and gas. What they found wasn't just warm dust, a classic sign of star formation, but blazing hot zones suggesting powerful bursts of localized energy. These hot spots might be the result of frequent supernova explosions or violent collisions between galaxies. But the intensity and frequency of such events implied that galactic mergers were happening much more often, and much earlier, than anyone had predicted. This high rate of merging throws a wrench into standard cosmological timelines. If galaxies were already colliding and combining at this pace, it means that cosmic structure must have started forming explosively fast. Instead of a slow and steady buildup, we're looking at a universe where matter collapsed into complex systems in a series of rapid, localized mini-big crunches. Even more unsettling were strange shifts in brightness detected in several early galaxies. These changes happened over short time periods, hinting at dynamic activity, maybe flickering quasars or powerful stellar flares. But what really caught scientists' attention was how synchronized these fluctuations were across enormous distances. This led to a provocative idea. What if the early universe experienced coordinated processes governed by unknown forces or fields that existed before cosmic inflation smoothed everything out? It's a theory that straddles the edge of quantum physics and cosmology, proposing that large-scale cosmic patterns may have been seeded by entangled conditions in the universe's first moments. On a different front, Webb made another startling find: the spectral fingerprints of complex carbon-based molecules, specifically polycyclic aromatic hydrocarbons, PAHs, in galaxies over 12.5 billion years old. These molecules are common today, but their detection this early in cosmic history was unexpected. Creating them requires a full cycle of star birth, death, and recycling, a process thought to take far more time than had passed since the Big Bang. Their presence suggests either that stellar evolution and chemical processing happened at lightning speed, or that the universe had some unknown pathways for forming organic molecules in its earliest epochs. In either case, it sparks a thrilling question. Was the chemistry necessary for life already underway, just a few 100 million years after the universe began? Even in its early stages, atmospheric research using the James Webb Space Telescope is already uncovering tantalizing clues. Webb has started analyzing the light that passes through the atmospheres of planets orbiting stars over 11 billion years old. Remarkably, one such world showed signs of a stable atmosphere containing both water vapor and carbon dioxide, making it the most ancient potentially habitable planet ever detected. Though still speculative, this suggests that life-friendly environments may have emerged much earlier in the universe's history than we ever imagined. It reframes the age-old question: are we alone? Maybe life didn't need billions of years to appear. Maybe it's been around far longer than we thought, possibly evolving or even migrating across the cosmos. And the implications don't stop there. Webb's discoveries are now pressing hard against the limits of our standard cosmological model, CDM, lambda cold dark matter. While this framework has been the foundation of modern cosmology, it's starting to show cracks. Scientists are proposing adjustments, different patterns of early density fluctuations, more efficient cooling processes for matter, and even tweaks to the way the universe may have expanded after the Big Bang. Some theorists are going even further, exploring the idea that gravity itself may have acted differently under the intense conditions of the early cosmos. Others are entertaining a more radical possibility. What if these ancient galactic structures aren't from our universe alone? What if they are remnants from a previous cosmic cycle, leftovers from a universe that collapsed and rebounded into the one we inhabit now? While still speculative and controversial, Webb's unprecedented observations are giving new weight to such bold ideas, not because they are proven, but because conventional theories are struggling to keep up. As Webb sharpens its focus and continues sending back extraordinary data, the pace of change in astronomy is accelerating. Every new image isn't just another clue, it's a reminder that the universe is deeper, wilder, and more intricate than we've been prepared to accept. The telescope has become a true disruptor, not by disproving old ideas outright, but by presenting clearer evidence of what's really out there. Its gold mirrors are revealing not just distant light, but deeper truths. Now, cosmologists are rushing to build new simulations that reflect Webb's findings. The latest experimental models explore everything from rapid cooling in gas clouds using non-standard chemistry to unusually high galaxy merger rates potentially triggered by modified gravity. Others are rethinking how black holes may have formed and grown in the earliest epochs. These theories are bold, unproven, risky, but they're essential because the rules of cosmic discovery have been rewritten. Universities that once built entire programs around the post-Hubble view of the universe are now revising their courses. Research journals are dedicating special issues to unpacking Webb's data. Interdisciplinary teams across physics, chemistry, philosophy, even metaphysics, are coming together to make sense of what this telescope is revealing. And still, Webb observes. Still it listens, gazing into the deepest past, gathering the ancient whispers of the cosmos. Light, shadow, motion, and mystery. What's most astonishing may not be what we've seen already, but what we're beginning to suspect. The unimaginable might not be rare. It might be everywhere. The universe is communicating in ancient patterns and cosmic structures, and James Webb is decoding its message with unrivaled clarity. What else is hidden in that distant light? Could there be early signs of intelligent life? Vast cosmic engineering? Traces of realities that existed before our own? As far-fetched as that sounds, the gap between science fiction and scientific fact has never been narrower. The James Webb Space Telescope has opened not just a new window on the cosmos, but a whole new chapter in how we understand our place in it. And the story it's telling? Far more astonishing than anyone ever dared imagine. What we once believed was a quiet, simple early universe is now revealed to be a turbulent crucible, brimming with energy, structure, and possibility. With every new stream of data returned from the James Webb Space Telescope, the early universe is being reimagined. Established timelines of cosmic evolution are being peeled back, revealing a tapestry of unexpected structures and interactions, calling for a complete rethinking of space, time, and even causality itself. One of Webb's most surprising discoveries is the detection of glowing halos of infrared light surrounding ancient galaxies, stretching well beyond their visible edges. These halos, rich in ionized gas, suggest powerful outflows triggered by intense cosmic events like hypernovae or extreme galactic winds. Their vast size and layered structure imply that early galaxies didn't simply grow in a straight line. Instead, they likely went through recurring cycles, violent bursts of star formation followed by explosive dispersals, forming a kind of cosmic feedback loop that regulated their own development. But that's just the beginning. Webb has also revealed colossal intergalactic bridges, long streams of hydrogen gas connecting galaxies that lie hundreds of thousands of light-years apart. These filaments seem to act as cosmic highways, feeding galaxies with fresh material and possibly even transporting stars and dark matter across vast distances. This challenges the view of galaxies as isolated islands and paints a picture of a universe deeply interconnected from its earliest days. In the hearts of some ancient galaxies, Webb spotted ultra-dense star clusters unlike anything we've seen before. Not only are these clusters massive and compact, but their stars span different ages, contradicting the idea that such clusters form in one explosive burst. This suggests rapid and repeated waves of star formation, pointing to a much more active early universe than theories had predicted. Webb's deep surveys also show that early galaxies aren't scattered randomly. Instead, they're arranged in a vast cosmic web, dense nodes and filaments that mirror the structure of today's universe. This suggests that the large-scale layout of the cosmos took shape incredibly early, perhaps seeded during inflation with more precision and speed than expected. At the same time, Webb is transforming our understanding of the universe's thermal history. Observations of faraway molecular clouds reveal surprisingly consistent temperatures, even at extreme distances in time. Instead of the patchy, chaotic heat we anticipated, the early cosmos appears thermally smooth. Some scientists now propose there may have been a hidden heating source, maybe early dark energy or a mysterious radiation field, that warmed the intergalactic medium far more efficiently than previously thought. There's more. Webb's polarization measurements, mapping the orientation of ancient light waves, have uncovered shockingly organized patterns. These may be caused by enormous magnetic fields or even large-scale distortions in space-time itself. One daring idea suggests these patterns could be remnants of a pre-inflationary era, cosmic fingerprints from a reality that existed before the Big Bang as we know it. As if that weren't enough, Webb also found starless regions in deep space, cold, dense clouds of molecular gas that haven't yet formed stars. These dark nurseries seem frozen in time, suggesting the rules of star formation may vary depending on local forces. Magnetic fields, turbulence, and the influence of dark matter could be holding them in delicate balance, like cosmic pressure cookers waiting for the spark of ignition. All of these discoveries point to a universe that is far more active, structured, and surprising in its infancy than anyone predicted. It's not just rewriting textbooks, it's reshaping how we think about existence itself. If you found this fascinating, hit the like button, subscribe to our channel, and share your thoughts in the comments. What do you think Webb will uncover next? Thanks for watching, and we'll see you in the next exploration.